The year is 2014. On a cold morning run, a friend of mine finds this horrifying statue in a ditch by the river and, for reasons unknown to this day, decides to gift it to me. You may be looking at this photo thinking, well, it looks like their heads fell off, and that's because the heads fell off the moment I brought it back to my apartment to show my roommates at the very gentlest touch. And I have attributed every single bad thing that has happened in our timeline the last 8 years to this incident. 2014 was also the year that I decided to shift all of my coursework to begin my foray into this new and exciting industry called cyber security. As an aside, after several years in this industry, this choice may actually also have been an after effect of the statue's curse. The jury is still out. I was extremely lucky to be placed in one of the early reverse engineering courses my university offered, and I had an incredible professor who truly taught us through doing. No written homework or written exams, just reversing and cracking programs from software we had all used before to some written custom by our own classmates. And one of the best exercises I remember we did as beginners was to tear apart old Windows games and see how many different things we could break and hack at. And to this day, I accredit his course to helping me understand facets of reverse engineering that aided me in finding my first job and still aid me today when I'm looking at different samples of things. And it absolutely pains me that I have no record of this professor's name in any of my documents, and I cannot for the life of me remember his name outside of, I think it was Brian. So Brian, if you are somehow out there watching this, thank you. Thank you for being an incredible mentor, even if you or I didn't know it at the time. Wait. Oh my God, did you think I meant you? Oh my God, Brian, you look at me. You really think you're the only professor out here named Brian? You taught Physics 101, and you didn't have a single meaningful interaction with any of your students. This is not inspiring, Brian. I didn't go into this much debt to answer why candle go out, Brian. Please just sit down. No, stop. Don't try to defend yourself here. Just sit down. This is so embarrassing for you. Anyway, in this video, I'm going to try to recreate the magic of being a beginner reverse engineer, poking and prodding at programs and games with you. If you choose to join me, we are going to dig into XP Solitaire's internals using Ghidra and x64 debug, find out some fun ways to hack and cheat at the game, explore how we can manipulate the graphics using Python, and I'm even going to show you how to quote-unquote weaponize the game to run your own code with C++. Perhaps pranking whoever still plays XP Solitaire. You can prank your grandma, who'll probably just call you to fix it. It doesn't matter. So if you're up for it, come with me as we hack and mod, build our reverse engineering skills and creativity, and have a ton of fun while we do it. I'm Jeff of all trades. Let's see if we can't master this one. A few important notes before we get started here. Some things that'll be necessary to know to understand this video fully and get the most out of it will be basic programming principles, and any programming language will do. The very basics about assembly language, things like how registers work, how the stack, heap, and addressing and pointers work. You don't need to know them in depth because we'll talk about a lot of those concepts throughout the video, but it will be very good for you to know those things to fully stay with us throughout the video. And lastly, hexadecimal, binary, and decimal are all going to be key to understanding a lot of the concepts we talk about. Some other stuff that'll be just nice to know will be any kind of disassembly if you've done it before, any kind of reverse engineering or debugging. If you have experience with C++ and Python, you'll also see a lot of familiar things towards the end of the video. But these are just nice to know. You don't need to know these things in depth in order to enjoy. And lastly, use what you learned from this video and all of your knowledge and skills for good always. Check the pinned comment of this video for updates and corrections, and if you have any feedback or questions for me, feel free to reach out here in a comment or DM, or on Mastodon, Reddit, or GitHub. All of those are posted to my YouTube channel. And of course, please like and subscribe if you enjoyed the content or got something great out of it. And please tell me what you would like to see me do in future videos. I hope you enjoy. Welcome. At this point, you've watched or skipped the introduction, and if you did skip it, hopefully you went back and looked at the important notes. And if you skipped those, then honestly, you're probably a person who often throws caution to the wind, and I wish I was more like you, to be honest, sometimes. Regardless, you've waited long enough. Let's go ahead and get into hacking and weaponizing Solitaire. Before we can do those things, of course, though, we need to get a copy of XP Solitaire. I've got my copy from the lovely Internet Archive at archive.org, and I will put this link and all the other links you'll see today in the video description if you need them. And I just downloaded the zip right from here. You saw it right here. So let's go ahead and extract that, and then we'll break it open in Ghidra. All right, once I have that extracted, I don't need the zip anymore, so I'll delete that. The zip from archive.org comes with Spider Solitaire and the cards.dll library, which by the end of this video we'll be very familiar with. And it's got the Solitaire executable as well. We're not going to be looking at the Spider Solitaire executable in this video, so if you want to hack at it, you can keep it around. I'm going to go ahead and delete it since I'm not going to be using it. And before we pop open Ghidra, one last thing to do is just make sure you can run the program and that it looks like it's behaving properly on your machine. And I'm getting a nice, smooth experience, blasted nostalgia, so that's looking good. All right, let's go ahead and open up Ghidra. If you do need to download Ghidra as well, or any of the tools we use today, again, I'm going to put links to those tools and their download pages in the description. I just got, as you can see, the newest build of Ghidra that was released a couple days ago, and it's going to do all the new things, so I want to disable tips on startup because I don't want to see that every time. And we'll be presented with the new project screen. So let's go ahead and add a new project. Non-shared project is fine. Let's go ahead and stick this in the same folder as our Solitaire folder, and we'll just call it Solitaire as well. Just keep the same theme. All right, now we can click the drag it icon, get our nice little Java animation there, and we'll be presented with the default workspace, which I'm actually going to clean this up a little bit. So I'm going to get rid of the scripting window. We won't need that. And let's go ahead and import our file before I mess around anymore. We'll get it from our Solitaire folder right here. It's going to just give us a confirmation that, hey, this is a x86 32-bit portable executable. Is that what you expected? We do, so we'll click OK. We'll just take a moment to load everything in. And at the end of that, we'll get a nice import results summary. And Ghidra will ask us, would you like me to analyze this file? And we would like that. We do not need any extra things beyond the defaults here. The defaults are honestly probably overkill for this little project that we're doing. But we'll go ahead and keep what's there, and we'll hit analyze. And we can go ahead and close out this confirmation window. You'll see the analysis progress going on down here. And it should only take a moment for it to finish up, just like that. All right, before we dig in, a couple other things I'm going to do just for my personal taste and for your comfort, based on some feedback I got from the Roller Coaster Tycoon video, is I know a lot of people had trouble seeing when it's kept at the default font size, and I agree, it's a little bit hard to see. So let's bump this up to 15, looks good. And we'll go ahead and bold it and apply. Oh yeah, that's looking very nice. Another little tidbit is you can see here, since I've enlarged the font a little bit, these fields are getting, why am I having such a hard time? They're getting cut off. I don't know why I was having such a hard time thinking of that phrase. To fix that issue, regardless of what you call it, what you can do is click on this little table icon right here, and then click on the field you want to expand out, and you'll see it pop up here in the bar. It'll highlight the field that you selected, And you can just take this little arrow in between those two boxes, pull it out as long as you want, and that way we can see a little bit more of the description without anything cutting off there. All right, with all of those creature comfort adjustments done, let's go ahead and get familiar with what we're looking at on the workspace here. So on the left-hand side, you've got different sections of the executable itself. You've got the headers of the executable, which is what we're looking at right now. The .text section, which has the brunt of the imported functions. The .data section that has all of the predefined data. Also, I should say a very important part of the .text section is not just the imported functions, but the actual code and functionality of the program itself is in that section as well. .data having all the hard-coded data in the program. And the .resource section, which has resources, which we'll take a look at later, but they include things like strings. If I scroll down here a little bit, you'll see icons, anything else the author may have embedded in the resource section. And then you'll also, in this example at least, you'll see the debug data and the TDB section of the executable as well. We won't need to worry about any of those sections. We'll primarily be working in these three right here in the middle, the .text, .data, and .resource sections. Right below that, you have the symbol tree, which explains some of the predefined function names, or I should say it doesn't explain them, but it displays them and allows you to go in and explore them. If I pop open the imports, we can, for example, look at the cards.dll library that was shipped with Solitaire. We can expand that out, and we can see exactly which functions were imported from that library. And if we click on them, it'll take us to that in the listing there. Same thing for not just functions, but labels for data and classes and such like that, which I won't expand out because there are quite a few. Data type managers down here, that has, as you would expect, data types. We won't need to worry too much about this view here in this video. It does show you what all data types are defined in the file, which can be useful. The big middle section here, of course, is our disassembly. So this has all of the, like I said, descriptions of the data and functions in the file. If we scroll down, we'll see some more assembly instructions here, which form the brunt of the file. And accidentally, but serendipitously, I clicked in there. And when I did that, you can see that when you click at a specific section in the listing here, you'll see the decompile window, which I have open here, start to spit out what looks like a rendering of this assembly code that is written in a higher level language like C or C++. So that's a nice little feature of Ghidra that I really like, is the decompiler view. Back to the middle section here, just to orient you a little more, you'll see from left to right here the address of the current line we're looking at in the file here. So if we go all the way back up, you'll see we start at address. Oh, I need to go try that again. Oh, I have the, so what's happening is I have the .text section selected up here. So if you just double click the very top of the tree here, you'll be able to scroll through all the sections. So now that I've done that, the very top address, the base address of the program as we call it, is 01 followed by 6 zeros. And then that address will show us for each line we look at where it is offset to that address. The next section there, the little blue numbers and letters here, are the hexadecimal representation of whatever the data is in the middle here. So for example, this is just a 2-byte structure that has 90 in hex. That's what that little H suffix is. It's telling you it's in hexadecimal versus decimal. So a 90 hex is stored in these 2 bytes, which we see here. One thing to pay attention to, and I talked about this a little bit in my Roller Coaster Tycoon video, and probably in the malware analysis, the async rat video as well, is to be careful for endianness, E-N-D-I-A-N, meaning we're looking at a little endianness architecture here, which means that the most significant bits are going to be in this leftmost side here. So how you should read a little endian, so like for example, this is a good example right here. The value is E8 in hex. However, if you look at the raw bytes on disk, they're going to read E8 followed by 3 zeros. In reality, these 3 zeros, you almost read it right to left. So this is prefixing that E8 byte, and then this is the final and most significant byte right there. It's a little confusing, but we'll look at a few more examples as we go through the disassembly that'll hopefully clear up that concept for you. You can also Google little and big endianness or watch some of the other videos that I put out where we talk about that a little bit. For the sake of getting through our initial listing, I'm going to stop talking about that and get to the rest of these fields. So let me find, let's go back down to the assembly for the rest of this. Here we go. So you'll see next to the bytes, you'll see the data. So down here, this is an instruction, assembly instruction, push, and then it's followed by whatever the operands are for that instruction. And on some lines, like for the strings and for the functions and subfunctions that are in here, you'll see this column to the right, which is called a cross-reference. That's what that XREF stands for. And that is just a address that refers to whatever is on this line. So, for example, this little snippet of a function here, at address 1003A7E, is referred to by, if I double click this line right here. So cross references are going to be very helpful. You can also hover like you just saw there and see that line right there references that without having to double click and actually skipping over to that line. And a lot of times you'll see it's very faint here, but you'll see this kind of commenting that Ghidra does when it has some context to add. So for example, this is showing us a data value. That is showing us the value that Ghidra has derived from looking at this data right here. And if I hover, you can see, or I guess I'll have to actually click because there's too much content there. But if you click on that, you'll see there's that data right there. Next to some cross-references, like right here, you'll see a function name. And that's showing you that this data is referenced in this function at this address. And then next to the colon here is the specific line in that function that refers to this data. You'll also see this blue R or orange W, and that means that if it's an R, it means that this data is written, or excuse me, I almost got it backwards. This data is read from this line in this function. And if you see the W, it just means that this data is written to by that function. And again, we already talked over the decompilation view. So with that, I think we have a better than average familiarity with the listing now. At least hopefully you do. With all that said, let's go back to the very top just so we don't get disoriented here. There we go. And let's reset and get ready to actually start doing some hacking. So as I talked about in the introduction, back in 2014 was when I had that course about reverse engineering, and I was really starting to be diving into it. And I was very much a beginner, still feel like a beginner to this day. It doesn't end. But something that has changed over time is I would, get an assignment, I would get a file to look at and hack away with. And it was very intimidating when you open up this view and you just see this disassembly and you have no idea where to start. And I'm sure some of you, if you're beginners, are feeling that right now. So my intent with this video is very much to take it slow, approach it as a beginner, trying to, channel my beginner as I was several years back, and try to ease some of that anxiety, I guess, by introducing you to some tips with using Ghidra and a little bit of workflow tips for how to go about reversing. So with that said, the first tip I have for you that was ingrained in me back when I was beginning, and I still use it to this day, is when we're just getting in, it's very intimidating to dive right into the code. So a better tactic is to go up to the window menu here, and let's look at the defined strings. So why do we start with strings? Well, strings, for those who may not be familiar with the concept, hopefully you are if you have some kind of programming experience, are simply predefined pieces of usually human-readable data in the file. So we see things like function names. We see things like, if I scroll towards the bottom, metadata about the file. What I like about starting with the strings first is it will draw our eyes naturally to points that we may be interested in depending on our objective in reversing this thing. So, for example, if we're reversing in order to hack this game, we may be interested in this score string or the time string, because if we go and home in on where that string is used, maybe we'll find out how to manipulate the score, because wherever the score is going to be, or wherever the score is going to be stored, is going to show up probably in proximity to the score string. Another thing, or another reason I like to start by looking at strings is I like to take a couple of these and just modify them and see what happens. And the reason I do that, I try to find something obvious that I can modify and just run the program and see if my modifications came through, because that will let me know fairly quickly if there's a middleman that's intercepting my changes if I make them to the file, or if something's going to break if I try to change something. So we'll do that in just a moment. Also, you may have seen another reason to look through the strings first is you might find some interesting tidbits that you otherwise would not see, like this series of strings right here saying, heck, I don't know, configure solitaire for screen, something. Again, if you use this button here and click on a field, you should be able to expand that out. Screenshots, interesting. Or, especially interesting to us who are trying to hack and mod the solitaire program, force a win. So you'll also find a number of interesting strings here as you're doing your initial exploration. We'll come back to those. For now, let's go back to that other concept I was talking about, which is let's find something fairly benign that we can change, and let's just see that we can confirm that our changes are coming through in the program itself. The string I'm going to start with is this copyright string right here. And there's a reason I'm going to start with this one versus another string. So let's go ahead and patch over it, which just means that we're simply going to edit that data and resave the file. To do that, we just have to right click or press Ctrl-Shift-H to patch the data. You'll get a nice little red box to show you that you're now changing the data. And Microsoft is not going to be super happy about this, but I'm just going to change this to say Jeff of all trades for the copyright and hit enter. And you'll see that the listing gets a little messy because we've kind of thrown off Ghidra from reading in the string. We've introduced some additional characters, and so it's cutting off this because it thinks that it's no longer part of the string. So that's something we just have to be aware of when you change data, is it might change the listing in turn. And also keep in mind that the changes we're making here, we're not going to see them in real time in the solitaire executable. What we actually have to do is go to File, Export Program, and we're going to choose the portable executable format because that's the file we're working with here. And I'll go ahead and save this to a new file called solmodded.exe. And we'll hit OK. We'll get a nice little confirmation here that our export was successful. And now, if we go open up our folder, we'll see our modded executable. So going back to the reason I chose this string is because sometimes you will look at a string and you'll think, oh, I have a general idea of where this might show up in the file. So the copyright string, for example, you may think, oh, that probably shows up in, maybe an about page for the program or in the top screen or something like that in the title bar. But sometimes what you have to be careful for is when you're modding strings is some strings are going to show up in the program itself, and others, like these, are metadata. And so they actually show up. If you right click here, and you'll have to forgive me, my computer's in Swedish, so hopefully if you don't speak Swedish, you can still follow along the pages here. This string shows up in the properties here under copyright. So this is something this is a change we wouldn't see necessarily if we just ran the program. It's actually embedded in this portion of the metadata itself. Now, if we actually try to run this program, interestingly, we'll get a error message because cards.dll was not found. It may seem obvious to some of you that that was never going to work because cards.dll is in this folder, not this one. I want to highlight that because we're going to come back to a way we can use that in our favor a little later on. But for now, let's go ahead and delete this modded file. And let's go ahead and change something else. And then this time we'll save it to the actual file that's, or a file that's in the folder with the cards.dll so we can actually run it. As far as next things to change, let's look at, again, something that's going to be fairly obvious to find, something fairly interesting. I have one actually in mind that we could look at, and you can filter, as you can see right here. You can filter on the strings here as well. This is the one I wanted. So this is another kind of metadata looking string, so developed for Microsoft by Wes Cherry. However, you'll notice that this string, unlike the actual copyright string we just worked with, does have a cross-reference. So this copyright string does not have a cross-reference. This string does have a cross-reference to a function in the program. That's another good hint to us as the reversers that this string is going to show up somewhere when we run the program. And if we want to know exactly where, well, we can click on the cross-reference. So we see, again, a little faintly, that string value is posted right here, and it's on a line that calls a function. But we don't actually see any reference to this address right here for the string or anything else. So how does Ghidra know that that is the string we're talking about? How does it know that it's being used right here? And if I look in the decompiler view at this function call, you also don't see anything immediately that points to that string. Well, it comes back to this other value that's next to the string down here. So keep in mind, if we look at this string right here, we are in the resource section. You won't see it immediately, but if I click on the resource section and hover over it even, you can see the address is 1008 followed by 3 zeros to 10, oops, let's see if I can get it back, to 100F9FF are all included in the resource section of the executable. And every resource or every string in the resource section has its own ID. And Ghidra is telling us that the ID of this string is 108, but keep in mind, this is in decimal. So if I take my calculator here, for those who don't know, you do have a programmer's calculator in the built-in Windows calculator, and it does translate between decimal, hex, octal, and binary, which is handy. If I put in 108 decimal, that is 6C in hexadecimal, which you'll notice, looking at the compiler view, is this value that was passed in that function. So that is how Ghidra knows that that is the string we're referring to, because it analyzed this section and it determined that this was a resource ID that was being pushed to this function here. Following along so far? So let's look at what this function is actually doing with that string ID. So let's go ahead and double click and open it up. And we see from the decompiler view, I'm going to pull this over a little bit just because we're going to be using the decompiler view more often than not than the assembly view. It's just a little nicer to work in and look at than the raw assembly. And we see that this function is very, very short. All it does is call the load string w function in turn, and it passes in the 3 parameters we passed in right here. Now, what is that load string w function? Well, you can just Google it, and you'll see me pull up pages like this throughout the video. These are right from the learn.microsoft.com documentation, where you can learn everything and more you ever wanted to about all of these different Windows functions. So load string w function loads a string resource from the executable file associated with a specified module and either copies the string into a buffer with a terminating null character or returns a read-only pointer to the string resource itself. So basically what it's doing is it's just loading in a string from that resource section. And if we go further into the page, we can see the function signature right here and the types and names of the arguments that it expects. So first parameter, excuse me, I said arguments, I meant parameter. First parameter being a handle to the instance of a module whose executable file contains a string resource, so basically a handle to the executable file itself. Now, before we go further, just focusing on that first parameter, the handle to the executable file, you can see that the first parameter being passed in Solitaire is this address right here. So if you see the dat prefix, that's a data, and then if we double click it, Ghidra will take us to that section where that data is defined, and you see a bunch of question marks. Why is that? Well, usually when you see that, it's because this data is actually defined at runtime, or it needs to wait until runtime to populate this for some reason. And that's the case going on here. Now, another cool little tidbit is you can, I don't know if cool is the right word, but another tidbit is you can actually relabel this now that we know how it's being used. You can right click and go to, whoops, let me get that out of there. Rename global, or you can click L as the keyboard shortcut to rename anything. Now, one thing you do have to be careful about with renaming a global, and in this case, I've already checked ahead of time, so I know that this piece of data is only ever used to hold that handle to the instance of the executable. There it is. It only ever holds this data, but one thing you have to be careful about is sometimes, it's not best practice, but sometimes some programs will use one global section of data for multiple different things. So if I relabel it something, I should have some confidence that nothing else but that something will be there. So for example, I'm going to enter H instance here because I know that throughout the lifetime of this program, it's only ever going to be H instance. But if I had another program that put, I don't know, the score in this section for some reason, in the same data where this handle was earlier in the program, that might be a reason I might want to be careful about labeling it one thing versus the other. Just don't box yourself in if you don't have to. But since I know ahead of time that that is, in fact, the only thing that's going to be ever held in that global, I'll call it H instance. Let's go ahead and relabel some others of these things while we're at it. Let me split up the screen here. And we'll get our load string W. Let's go ahead and rename some of these parameters because we know for a fact that these will always be only used for these items. So I'll call that UID. We'll call that LP buffer. So that's, again, if you're looking over here, that UID is the identifier of the string to be loaded. So that's that hex 6C value we saw. The next parameter is the buffer to receive whatever's in that string resource. And the last thing is the size of the buffer in characters. So we'll go ahead and label that as well. And let's go ahead and also, since this function only does one small thing, let's just go ahead and rename this function so that if we see it again, we'll know exactly what it does. So we'll just say passes to load string. We'll just call it that. So now, let me blow this back up. We'll not only see that change in labels here, but if I back off to where we were before, where this function was called, right here, you can see that the label came through. Now, the parameter label did not necessarily, but we can edit that label right here. So this local underscore D4 was defined in this function. A good way to find any variables you're looking for in more than one space is to right-click, secondary highlight, set highlight, and Ghidra will highlight every other place that that variable name shows up. So you can see right below here, D4 is used. And honestly, in those two lines, that's the only two places that that variable is used, aside from at the very tippy top here, where it's defined as a character array of the size 100. So because we know that it's not being used anywhere outside of these two functions, which we'll talk about this next one in just a moment, let's go ahead and rename it in this space as well. And we'll just rename it to, we'll say string buffer, because that's what it's being treated as. Perfect. And in fact, we can be more specific because we know that this string that it's loading into that buffer is in fact our, what was it, developed for Microsoft by blah, blah, blah. Let's go ahead and call it something more specific like author string, because Wes Cherry, the author, is mentioned in that string. Whoops, I misclicked there. All right, so we know what's going on now with this passes to load string function. It's getting that specific string from the resources that has that developed for Microsoft, blah, 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 Wes Cherry. Let's talk about this next function here, ShellAbout W. Now, just from the name, you could probably guess what this function is, but let's go ahead and do what we did before and pretend we Googled it, and we can see that it displays a ShellAbout dialog box. Pretty straightforward and self-explanatory, but what does that actually look like? If you Google what a ShellAbout dialog looks like, it's this generic about screen that you've probably seen on several different Microsoft, at least, programs that you've run before, including Windows itself. So it has a very standard kind of format, and it makes sense that we would see the author string showing up here. Now that we're armed with that knowledge, we can change that develop by string, and we can now know that it's going to show up in the about box, and we can go check to make sure that our changes are working as we expect by running our program and going in and making sure that string changes. So let's go ahead and rename all these variables as well, just to get some practice with that and to help us out later on. The first parameter is the handle to the window. So let's go ahead, oops, I pressed the wrong button. Let's do label. We'll call that HWND. The next one is another data section here. That is a pointer to a null terminated string that contains the text to be displayed in the title bar. So let's go ahead and rename that to, they call it SZApp. I'm just going to say window title. I think it's a little more appropriate. Author string is already defined there. And then the last thing is the icon. So let's rename that Hijacking. So one thing I do want to touch on that last parameter, the icon. If you want to know which icon is being used, how might you go about doing that? Like, let's say you wanted to manipulate which icon was being displayed in this about dialog. Let's double click on this, and we see that Hicon is also undefined, but Ghidra shows us where it is written to. That's what that tiny w is, if you remember, in the file. So let's go to where it's written to, and we see it is, so what you're seeing actually is a little bit of a weird, I don't know if I'd call it a bug, but a little bit of a nuisance with Ghidra is sometimes when you double click on a reference or a cross-reference, your decompile view will not catch up to where your assembler view is. So if you just click in this middle window here, there we go. Now it's kind of caught up to where we're looking. Here's where Hicon is loaded, and it looks very similar to the load string w function. You see we're passing in the H instance. Thanks to our labeling, we can see exactly what that is. And then we get another code, 0x1f4. That 0x is just a prefix, meaning this is hex. So 1f4 is what we're looking at. So if we wanted to know which icon was being pulled, what we could do is search for scalar. And we're going to search for a specific scalar, 0x1f4, and again, be careful if you're searching to, if you're intending to search a hex value, make sure you include the 0x before that. And if you're intending to search a decimal value like 15, you don't have to include any prefix there. I could just type 15. But we want 0x1f4. There we go. Also be careful, because I highlighted something here, it's going to try to search the selection. I actually want to search everything. And we see a few results. So let's go ahead, let me see if I can pin this. All right, there we go, sorry about that. So what I did there is, well, I can't recreate the window being unpinned now, but I just took the title bar here, dragged it over here, and that'll kind of pin it down in this window over here. So we see a few references to that 0x1f4. We see it right here where we're looking at load icon, and we also see it down here in this resource section once again. And it shows up in this very odd looking, let me expand this out a little bit, this very odd looking structure called an image resource directory entry name struct, which is a mouthful. So I'm going to include a little bonus chapter at the end of the video for those who are truly nerdy and care about this stuff and want to get a little more in the weeds with reversing. But there's a way you can actually take the structure and reverse engineer exactly which resource this is talking about. Now, for the rest of you who don't want to do that bonus chapter or maybe not interested in the details there is an easy button that Ghidra gives us for finding which icon this is referring to. And to find it, I'm going to move back up to that load icon section just to start from a clean area. And the answer to that comes back to the difference between a scalar search and, if I go up here to search, the program text. So the scalar search is really looking for data that's defined in the program itself, whereas the program text is looking not only at that data that's in the program, that's in the executable, like defined as a scalar like this, but also it's looking at the names of things like functions, labels, mnemonics, and other things that Ghidra has already picked up for us. So we can select specific fields, or we can choose all fields here. And again, make sure you don't have search selection selected. And I'm just going to search for 1F4 and search all. And we get quite a few results because we're seeing everything that has the characters 1F4 in it, as we expect. And if we scroll down here, we'll see at the very bottom, there is another resource that is called, resource GroupIcon 1F4409. And again, I'll discuss this a little more in the bonus chapter that I'll have at the end of the video. But what this is saying is that this resource has an ID of 1F4, and the 409, which you'll see across all of these resources here, is actually a language code for English. That's why you keep seeing that over and over here. It's telling it what language the resource is in. So all of that detour to say that the icon being loaded into that about screen, you can reverse engineer it by looking at what ID is being used in that load icon call. And going back, you can see it's a group icon resource, which what the heck is that? Well, I have a nice little blog that kind of talks about that from Raymond Chen from a little bit ago, a little bit being 10 years ago, where he talks about icon resources and group icon resources. And the long story short of it, the too long didn't read, is that when you have a group icon resource, what it does, and it being your computer, is it looks at the icon group, which includes all of these above icons, and it decides based on the type of machine you have and the type of maybe, your graphic settings or whatever, what you can support, it'll automatically choose the icon image that best fits your machine. So for example, if I'm running this with a older machine, I might get one of these low res icons. If I run it with a newer machine, I'll get the high res icon, depending on the context. So now that we've talked through that, and you may not have even cared to know anything about the icon in the ShellAbout call, but there you go. It is important to know kind of how these things piece together as a reverser, just so you know and have a clear understanding of the program flow. So let's go all the way back to where we started with the ShellAbout call. And let's get back to our original objective, which is let's just edit this author string and make sure that the changes we make to the program are coming through okay. And let's once again patch the data and put something else here. Sorry, Wes. We appreciate your hard work. All of us in grade school, computer labs everywhere. Okay, cool. So I'm actually glad that this error happened here. So this is something I've noticed with Ghidra. I don't know if this is intentional or not with the patch data action, but every now and then you'll get this exception, which means something went wrong with Ghidra itself. That happens, I think, because we're patching in this screen here. And the way I've learned to work around that is there's actually another way you can patch data, and that's by going to Window, bytes. And this is going to show us the raw byte view of the executable right here. And if we go to click this icon, actually, I think there's, now that I'm looking at this, I think there's actually another view. Oh yeah, here we go. So up here, if you select your settings, you can also put the ASCII view on there. And this is a little nice to work with because it'll show you not only the raw hexadecimal bytes, but it will show you the text there. So let's go ahead, if you click on this little pencil icon, we can start overwriting this data just by typing right here. Now these are Unicode strings, as you can see by that P Unicode label. And what that means is there's going to be a null byte in between each character. So we do have to keep that in mind. So I'll just be very careful in editing. Oops, except I wasn't that careful, I guess, because I just skipped over a byte. So let's go ahead and fill that back up. You know what? I'm just going to keep it at Jeff because we get it. We get the idea. Too long to type out everything else. And we'll just null byte over everything else there. That looks good. So once we do that, once again, we're going to, except I might have put, did I put an extra space? I did. So let's change this to 66. Oops. Go back into edit, 66, null byte. There we go. That's looking better. And you can see those null bytes actually show up in this string here now. So let's go ahead and, as we did before, let's export our changed program. But this time, let's put it in this folder so that it picks up cards.dll. And we'll call it, again, solmodded.exe. And this time, we should be able to actually run it. And there we go. So as we said, we expect to find this in an About screen. And if we look in the menus here, we see this About Solitaire option. And look at that. Now I am blurring out the bottom there because it has my email address, so I don't want that out there. Sorry, guys. And we see that this has the developer Microsoft by Jeff right there in the middle. So we can see that nothing is messing with our ability to change the data. There doesn't seem to be, in some programs you might see defense mechanisms to prevent people from modifying data. But in this case, which was expected for a decades-old program, we don't see anything like that. So now that we've confirmed our hypothesis, I know it took us a long time to get there, we can finally start doing some fun stuff, like messing with the score and trying to actually cheat at the game. So when it comes to modifying, let's start with the score, because obviously if I'm a game hacker, that's going to be what I'm most interested in. Oops, I didn't mean to close my string view there. There we go. Let's look at, if we just type in score as a string, we see the score, with a colon. And if we look at the cross references there, we can see that that is loaded into the passes to load string function here. But that's followed by a lot of other stuff going on here. And the problem with looking at this score colon string in particular is it's not really telling us a lot about where the actual score value is coming from, meaning the actual points that the player is getting. Where's that value stored? So this doesn't appear to be very helpful. Now what we can do is go ahead and label this string here to say this is a score buffer. Now if we go look at where the score buffer is used outside of the place we just saw it, we see it's also used, let's see, right here in this function where it's passing with the variable. So you might think, oh, well, this might be where the actual score value comes in. We can click in the function. And we can certainly see that there is some math going on here, but it doesn't look quite like a scoring function. And you may not know that just by looking at the assembly or decompilation right away. You could open up a debugger, which we can take a look at this in the debugger when we use it in just a bit. But I can tell you that this is probably not the scoring function and doesn't have anything to do with the actual score value just because of the type of math going on here. We see that something's being incremented for sure, but it's doing it in a loop. And the reason I say that that doesn't seem like the right scoring is if you aren't familiar with solitaire scoring, I'll open up this page right here where you can see the scoring system. And that is, in standard scoring, you don't just get 1 point at any time. So you never see the score go up by 1 point. You'd see it go up by 3 points or 5 points or 10 points for cards moved to the suit stack, or negative points. So that's what leads me to believe that that function is not the one we're looking at, which, again, the goal of this is to find where the actual points value are being stored so we can hack that and either adjust the scoring system ourselves or adjust the score ourselves in such a way that we can win faster, or just show off to our friends that we can do that kind of thing. So what we'll do is we'll back off from that and let's brainstorm some other ways we might be able to find the score. Now, unfortunately, if you look at the term score, that is the only defined string where we see score as a value come up. However, this is another little gotcha in Ghidra, is that if you just stick to the defined string window, it's only going to be looking at what it thinks are strings that are defined in the program listing, but sometimes it misses a few. And what I mean by that is sometimes, again, if you go back up to search, and let's go to program text again and search for score. Search all. We actually see, there it is, a couple other things that have the word score in them. So we see, for example, scoring down here. And the reason this didn't come up is because if we, oops, let me scroll down the other way. This shows up not quite as what Ghidra would consider a defined string, because it shows up in an item title structure, basically. I think that's why Ghidra at least is leaving it out of our defined strings view. So again, another way you can find some extra things that you may not see in these predefined views is just by searching program text or memory or for instruction patterns or any one of these search functions. Now, if you search just for strings, this is going to do the same thing, I think, as the, well, actually, hold on. Does it come up in here? Okay, so I stand corrected as we do it live. It actually will show you that this scoring item does come up there as opposed to defined strings. Now, why they don't include all those strings in here, I don't know if it's by design or, you know, they're just choosing to omit them for some reason, but just be aware that you may not be getting the full picture by looking at this alone. So how does this help us, though, just to see this scoring string? Well, if we look down here, we'll see some familiar terms. We'll see scoring, standard, Vegas, and none. So if we go back to that page I just popped open, you can see that there's typically two scoring systems, standard, Vegas, and then of course none means none is involved there. Now that is an interesting prospect for me, having no scoring system involved as a hacker, because if I can convince the game to stop adding my score up or stop detracting my score, is more likely, maybe I can cheat at the game and only get my score to go up. And the way we can do that is look at what happens when scoring is set to none in the program, because when scoring is set to none, it's going to obviously not take away or add any points. And if I explore how it does that, I might gain a better understanding of how scoring is implemented, and I might be able to tweak this a little bit to only allow me to gain points and not subtract points. So how might we do something like that? Well, we start by, you can't really see it, I'm noticing it's cutting off. There we go, I just had to click over a little bit to show that box with the plus sign in it. We could expand out some of these fields, and we may not fully understand them. In fact, let's go ahead and open up the documentation for dialog item template structure, and it will tell us that this is a structure that defines the dimensions and styles of a control in a dialog box. Okay, so that's interesting. Wherever the scoring is defined, it should be in a dialog box. So basically that means like a pop-up box. And then it goes on to explain one or more of these structures are combined with a dialog template structure to form a standard template for a dialog box. Most importantly, if we read through here, we see all of the different parameters that are, or all of the different, I'll say, attributes that are part of this structure. And at the very bottom, we see that there should be an ID included. So let's home in on that a little bit. If we open up the dialog item template that is right above our none string here, we can see that it has an ID of 130 hex. So you know the drill by now. Let's go through and search for 130 hex. And we see it show up in actually a few spots. So let's start from where we're at now. We see it right here defined in this section. Go ahead and get rid of that. And by the way, we are, in case you didn't notice, we're back in the resource section. That's where this is defined. And if we go up to the next spot, let's see where what this is that's being referenced. So where's my 130 hex? Right here. Let's see if I can get the decompile view. Am I blind? Am I just not seeing it? What am I missing here? I see 133. I see 134. Oh, there we go. Yep, it just took it a minute I had to click around a little bit, like I said, to catch up. So we see 130 hex referenced right here in this check radio button function. Interesting. Okay, so what the heck is check radio button? Let's go find out. There we go. So this can be a little confusing here because check radio button might sound like the verb to check something, as in to check the value of something. But in fact, it looks like this function actually adds a check mark to or checks a specified radio button. Kind of a poor naming scheme in my opinion, but we'll go with it. So this is adding a check mark to a particular radio button that shows up in a dialog box. And in case you're not familiar, a radio button, let's just go ahead and just Google what that looks like. You can see that a radio button is just one of these selectors that looks like this. So you have multiple choices and you can select any one of them, but just one of them. So that's what a radio button, that's what we're talking about here. So let's look at the parameters again. Again, we have a handle to a dialog box, and then we have the identifier of the first radio button in the group, the identifier of the last radio button in the group, the identifier of the radio button to select. So that is good context. Let's pull that up side by side with our code browser here. And we can see that this param1 is, we'll go ahead and rename that. That's going to be our dialog box itself. This is going to be the ID of the first button in this dialog box, and this is going to be the ID of the last button in that dialog section, I should say. And the one we're checking is stored in this data value right here, which is predefined as 12E hex. So that's this guy right here. So let's go ahead and name that. Actually, before we name it, let's go back and look at what that identifier actually is. So let's go back to where we were looking at the none string down here. And if we go poke around through, we could search for it, but they tend to be in numeric order. So if we just move up, we can see that the Vegas string is 12F and the dialog string here is 12E. Also, you may be wondering why that ampersand is showing up in the middle of standard there. I'm honestly not sure. If anyone has an idea, I don't know if that's a rendering issue or if that's intentional. I'm not sure why that's showing up as an ampersand. But the moral of the story is that 12E is standard, 12F is Vegas, 130 is none. So putting this together, our first button in the series should be that standard button. The last button should be the none. And then this was 12E. So again, that is the standard scoring string. Oops, I didn't mean to comment, but rather add a label called standard. This does bring up a good point, and I should have brought it up earlier in the orientation to Ghidra, but you can also select semicolon. And you can put comments in for when you need a little bit more room. So if I wanted to put a comment at the end of this line, for example, I could say ELL comment here. And you'd see it come up in the listing there. So if I didn't want to label something, but I still wanted to add a little note to myself about what something does, I could make a comment there. Sorry, I just want to point that out since I accidentally keep pressing that semicolon, which is the shortcut for that. So with all this newfound knowledge, what we can do now is go to actually run our program and confirm what we are deducing from the assembly here. So let's go up here and we can just poke around the menus, and I think the obvious place we would see the scoring mode would be the option screen. And sure enough, just as we predicted from looking at nothing but the decompilation and disassembly, here are the 3 radio buttons. Standard is the one that gets checked by default, and you can also select Vegas and none. However, even though it's really cool that we were able to deduce that by ourselves, it doesn't quite get us closer to understanding what happens with the scoring or where the score value is stored so that we can manipulate it. So let's keep digging. Let's go back to where we had our scalar search of where that none score showed up. So the next place is, again, up here. So, oh wait, was that the one we just looked at? I feel like there was one. There are 2 places actually that it shows up here. Oh yeah, so it shows up further down here, but it's the same deal. It's just checking that radio button right there. And then we have a few places where we have comparisons. So, oh, this is a good example of mislabeling. So I labeled that standard because that was the default value of this data structure. But right here, we see that that data structure is compared with the value for none mode of scoring. So maybe a more accurate value or label for that would be score mode. It's a perfect example that I accidentally gave myself of why you should be careful with your labeling before you fully understand what it is. And actually that cleared up this listing a lot. So you can see based on the score mode, different things will happen in the program. And we may not fully understand what's going on exactly right here, but it gets us closer. And let's see, if we go to these others, these are in pretty close proximity to the other one. So here's another function. It's interesting because if the score mode is set to none, it returns right away. So this might be an interesting candidate because maybe this does something with the score if the score mode is not none. So if it's standard or Vegas, maybe this is the one that edits the score. We don't know for certain. If we go to the next entry for where that value shows up, here's another one for if the score mode is not none, it starts manipulating some data based on some parameters. But again, we're not intending to go through and fully understand each of these yet, because it can be a little tricky to do that just looking at the assembly itself. I'm going to show you a little bit easier way to do that. And then the final place we see that come up is in this section. And what's interesting about this section is it's actually setting the score mode. So this must be the function that's called, and let's go ahead and label it as such. Something like set score options. And maybe more generically, we'll just say set options because we don't know. There might be more than the score mode being set here. It sure looks like it. Now, as an aside, what's kind of interesting here is if you look up here at this function where, so let's just back up here. So the score mode is set based on, the value of uvar2. So let's label that decides score mode. And we can see that that value comes itself from this pH var1, which we don't know what that is. So I'm not going to label it right away because it's also being used to set a few other things, which again, we don't know without context what those things are. We don't really need to know. So where does that value come from? It comes from whatever the return result of this function is. So if we click into this function, oh, interesting. This function is talking about a registry key. And what might be a little confusing, I should say, is if you look at the actual function definition for reg create key, it doesn't just create them, it also will open the key if it already exists. So why am I taking the time to talk about this? Well, this is a cool little nugget that as reversers, we might have just stumbled upon that tells us something about how the options are stored and helps us understand a little bit more about how we might manipulate the program. Because what this is telling me, if we look at the parameters in here, is that this option that's being returned is being derived from a specific registry key. So if we wanted to confirm this, we could go to this specific registry key in our registry editor. Now, if we look at reg create key, that first H key parameter that's passed in there is a reference to one of the hives. So those top level folders that contain those registry keys. So if I open, let me just go ahead and open regedit. So in my registry editor, I've gone to H key current user. I'll show you how I got that in just a second. And there we go. I've opened up that key, software Microsoft Solitaire, and right here we can see there's sure enough an option string right here. So let's try to see if we can confirm when we run the program and change that option if the registry actually changes. So let's change this to Vegas scoring, and we may need to, I thought there was a way you could just refresh it there. Maybe it's in here. There we go. Should be F5. And sure enough, we see the option string changed to 13 hex. We change it to none. Let's refresh again. It's now 23 hex. So again, maybe not pertinent to the objectives we have for just manipulating the scoring, but good to know that if we did want to do something with hacking or modding the options, it's all derived from whatever's in the registry, which is pretty cool. All right, let's close out of all of that. I wanted to touch on this value here. So the reason or the way I was able to find that was H key current user is just through a simple Google search of that value and H key, and it was one of the first ones that came up, not in malware here, but yep, right here. And it's just some random GitHub repo, but it did the trick. I was able to see that that was the value that was mapped there. I'm sure there's somewhere in Microsoft's mountain of documentation it's also recorded somewhere too. Maybe, I don't know. All right, getting back on track to our original objective, we again see that we have these other spots. So we can rule out this function because it's actually not, it's only setting the score mode. It's not actually contributing to the score itself. So we're left with these three functions that we really don't fully understand what they do yet, but they all check the mode of the scoring. And if it's none, it changes the behavior a little bit. It looks like for those two, it straight up just returns and doesn't do anything. And for this last one, looks like it modifies a few different things here. But again, without diving into get text extent point, and we can speculate that this is probably drawing text on the window somewhere. But without getting into all of this stuff, we may not fully understand what's changing here, and it may take a while to dig through that. So a good shortcut is to now break open our debugger. I'm going to be using x32 debug or x64 debug. I'm using the 32-bit version because it's a 32-bit executable, but I'll leave a link to x64 debug, which is kind of the main version that is marketed. And this is, as you can imagine, a debugger. What that means is we can go ahead and load our Solitaire program in here, and we can now manipulate the data as the program runs, and we can see what values different addresses take on. And it's going to be very useful for us because what we can do now is take a look at each one of these functions where the score mode is checked. So let's start with this one. This check happens in function 101, or excuse me, 01005203. So let's copy that. And I should probably do a side by side here so it's easier to copy, paste back and forth. By hitting Control G or enter, or you can also right click and go to in here. I think it's right click, go to right here. And you can select expression. We can paste in that address and it will take us to where that function begins. So if we do a one-to-one side-by-side comparison of our debugger now and what's in Ghidra, we can see that these are the same instructions. But the cool thing about using the debugger is instead of going through the guesswork of looking through the assembly and trying to figure out what this function is doing, we can right-click, set a breakpoint so that, oops, I didn't mean to do a conditional breakpoint, just a toggle. And you can also hit F2 to trigger that. What this will do is every time while the program is running, every time this function is triggered, it's going to pause the program in the debugger and let us go in and actually step through the commands one by one. So since we had 3 places that we weren't really sure about, let's go ahead and add all 3 of those functions into our breakpoint list. So this one occurs in, just make sure, this guy right here. So we'll copy there, and once again we can paste that, oops, without the function prefix into here. And oh, I wanted actually the start of this function, thank you. I thought that was the start, but I could be wrong. Yeah, 505, oh yeah, it is the start. Yep, that's just the first command that's run is that compare. Okay, we're good. So let's hit breakpoint. And lastly, the last one is, get my taskbar to behave. This function right here, 0100306F. Let's put that in and add a breakpoint. So we've got those loaded in. Let's go ahead and blow out our debugger here. Now, we can see already we've hit one of the breakpoints. So let's go ahead. I'm sorry, the taskbar keeps popping up there. In the bottom left there, you'll see it says paused, and it says int3 breakpoint at that address. So I'm going to hit continue because I'm not quite ready to go look at what's in that function. What I really wanted to do, actually this is good feedback, is, oh, now it might have frozen up my debugger. All right, actually before we get started with the breakpoints, sorry, my taskbar kept getting in the way there, so I had to pause to flip that real quick. Let's right click and disable all these in the breakpoint view here. And what that's going to do is it's just going to let the program run. First we have to click run, this little play button up here, or click F9 on your keyboard. Because what I wanted to do first is manipulate the options, because right now we have scoring to none. Well, what I wanted to do is actually flip our perspective from now hunting down where that none mode is being used so we could get an idea of where the scores take into account. And now switch it just to standard, because now we're going to be able to see that score or that point value in real time. So our goal here is to figure out where this score is being pulled from so that we can manipulate it, whether that means adding to it or changing the default values of what the score should be, or making it so that we never have a negative score, because by default, again, by standard rules, I just got 10 points for pushing a card up here and another 5 points for flipping a card, but every 10 seconds, 2 points are deducted. So as a hacker, it'd be real cool if I could either make my point level so high that it doesn't matter that my score is being deducted, or disable the deduction altogether by disabling the timer, for example. So let's explore. Let's turn these breakpoints on and let's explore what happens every time the score is manipulated. So right away we hit a breakpoint. I can't bring the window back up because, there we go, I'll just pull this over, yeah, up here if I can. And I'll put my Solitaire window there. It's not liking me clicking on that window because it's not going to be responsive because the program's paused right here. So another little tip here, now that we know that this function is being paused on with our breakpoint. This was the longest of the 3 functions we were looking at, and therefore it's probably going to be the most complicated to figure out where the score is being pulled from for this function. So, and we'll notice that if I go ahead and hit play again, it's already hit that breakpoint another time. Even though nothing, sorry, the window's freaking out a little bit because it keeps breaking on that point. Even though our score shouldn't have changed because 10 seconds hasn't passed and we haven't done any actions to gain points, so we shouldn't be gaining or losing points, that breakpoint is being hit, which tells me, along with the fact of looking at this assembly and seeing it's talking about font and text without knowing exactly what this is doing, I have a feeling that this function is just being called every second because it's probably drawing the score down here, and that's why it's referencing the score mode. Because if the score mode is none, and again, I haven't looked through this assembly at all, but I'm assuming what that's checking for is if it should even paint the score mode at all. And so this function may not be as useful to us because it's going to pause our program every second. Every time I click play, it just pauses it again. So let's get rid of that candidate and let's move on and see if the other 2 functions hit. And that one did. So this is the 306F function. Let's take a look at what that one was. It's going to be this guy right here. So this one, there we go, checks to see if the score mode is none, and then based on this param2 value, it calls another function and does some manipulation of the other parameters there. So real quick, before we dive into the assembly and verify what this is doing, let's hit play. Oops, it's because I keep dragging my, keep trying to pull it over, keeps moving it. I want to point out one thing here before we move on. Is that breakpoint hit after 10 seconds had passed. And so keep an eye on the score value here. Now you see this is the function that's getting called. Let's try to actually gain some points. Let me wait for the next 10 seconds so that it goes down again. And then I'm going to try to gain points and see if it's also called. So let's move this over to the jack and flip this card. So actually, without even flipping the card, this 505F function was called. So that was the other one we had seen right here. All right, there we go. Sorry about that. I had to cut away to start a new game so I could get some better cards to get some quick points with. So going back to what we're observing here, we see that this 306F function is called every time we decrement our score, as well as every time we score points. Now, the other one that was called, let's say if I move this queen over to this king, this 505F function is called every time we gain points. But watch, if I let it run for 10 more seconds, that function will not be called at all. We'll go right to 306F. So I'm going to focus my energy on this function first because this appears to be the one that's called whether we're gaining or losing points, and so it's likely to be closer to the source of whatever part of the program is holding our actual score, so that we might be able to manipulate it. So to go through and try to figure out what's going on here, let's first look at the Ghidra view. So right here, we already know we check to see if the score system is, or the score mode is none. And depending on this parameter that's passed here, and maybe we just call this something like flag. Depending on the flag, 3 different tracks are taken here. So if the flag is -4, then we end up calling a function and passing in this parameter here and this parameter here. Let's take a look at what this little mini function is here. So very simple function here. if the first parameter is less than or equal to the second parameter, it just assigns the first parameter that value. Let's back up here. And then the result of that function gets assigned back to, so this piece right here is saying that this is an integer pointer. So an address that points to an integer. If you're not familiar with the concept of pointers, highly recommend you read up on them. So this tells me that this param1 is probably a data address in the file. So let's label it as such. I'll just say data address. And so if after that function's called, depending on which one of these is selected from that function, that gets passed to ivar1. If, on the other hand, the flag is -3, then we simply add whatever's at this data address plus 30 hex to whatever this parameter is. And lastly, if the flag is not -2, we return out of there. And I assume if it's -2, we just set that data address to param3. So this is a little bit confusing to look at in Ghidra, as I'm sure you've seen, because we don't exactly know. We can see that this is a data address. We can see that this param is being added to whatever's at that data address. Maybe it's the score, but what will help us is going back into our debugger and actually walking through the parameters as they come in here. So we are broken at the start of this function, and we can see the parameters right here. So for those who may be unfamiliar with how the stack works, the first thing that will be pushed on the stack right here in the bottom right is going to be our return pointer to whatever function called us from here. So right now we see our return pointer is set to 10031DA, which is, if I go back to Ghidra, and you could do this, I guess I'll show you how to do it in the debugger first. You can go to 10031DA and see that sure enough, right before that, we got called to the function we're broken on. So this is just storing on the stack where we're going to return to after this function is done. Now, right below that on the stack are our parameters. So this is going to be our data address parameter. This is going to be our flag. And this is going to be our param3 value. So what's up with, so this one is just a data address, which we can, if I click over here into the dump screen, which is just showing a memory dump of the process that's running, I can type in that address and see what data is at there now. And as far as I can tell right here, it looks like a bunch of gibberish, right? And then this is our flag, which we know should be in the realm of -4, -3, -2, maybe some other value. But what's up with that hex code that's right there? So you see 7 Fs and then C. Well, to understand this, if you haven't seen it before, if you haven't done a lot of kind of lower level programming, you may not know about this thing called 2's complement. And basically it's just a shortcut way of representing negative numbers in just a single byte. So I'll leave this resource in the links in the description for you if you're interested in learning more about it. But all 2's complement is, to put it simply, is saying that if I change my calculator here to just be a word, which is, or even, no, just a byte, we'll just make it a byte. If I have a regular positive number like 5 in decimal, that shows up like this in binary. If I do 55, it shows up like that. And you'll notice that no matter how high I go, let's say I go up to, let me get the max value here that I can. So just for a byte, it's going to be something like 7F. So 7F is 127 in decimal. And that you can see down here, all the bits are set to 1 except for this final one. Now watch what happens when I increment this to FF, which is setting all the bits at once. it changes decimal to -1. Why is that? Well, the rule of 2's complement says that if this first bit is set, we interpret the rest of the number as negative. And the way you, the human, or the computer can determine that this is -1 is to simply flip the bits and add 1. So if I flip this, I can do that by doing a not on the calculator. I get 0, add 1, and that tells me that it was -1. So if I take -5, I'll just hit the positive negative symbol right here. We see that -5 is represented as this bit set right here. And if we not this and add 1, we get decimal 5 back. So it's a little bit confusing if you haven't seen it before, but in principle, it's actually a very simple concept. It's just a way to represent in bytes a negative number. So what that means for us is anytime we see a number that starts with 7 Fs, let me boost this up to a word, which is 2 bytes, which is what we're working with in this Solitaire program. So let's open up our debugger here. We see that the second parameter is FF, FF, FFFC. So if I do 7 Fs, oops, sorry, it's not a word, it's a D word actually. So we're looking at altogether 1, 2, 3, 4 bytes in length for 32-bit. So let's change that to 7 Fs. And we see that in decimal, that is in fact a flag of -4. All right, so now that we know what these parameters are, let's go back to, before we go into the debugger, let's go back to the listing and kind of walk through mentally where we think this is going to go. So we know our flag is -4, and we know our param3 is -2. Now, I want to point out something interesting with this little mini function we looked at here before. The second parameter is always 0. So if we go back and investigate, whatever our first parameter is, which is going to be that address plus -2, so that address, whatever value is at that address -2, it's going to be compared to 0. So if that value is less than or equal to, in fact, let's label this 0, it's going to be set to 0. Otherwise, we just return the value. So all this function is doing is seeing if this is a negative number, and if it is a negative number, it's just setting it to 0. Now, can you think of why we might want to do that? Well, if this is in fact the scoring mechanism, we typically wouldn't want a player to get a negative score. And so this is a fail-safe to make sure that if we ever get to the point where the player is getting negative points, we just set it back to 0. That's what we're hypothesizing. Let's see if we can confirm that by looking at our score and this function in the debugger. So what I'm going to do is I'm actually going to let this run, and I'm going to start a new game. So let's go ahead and restart our debugger session, hit run. Oh, there we go. I just had to click in. Sorry, I restarted the game. I just learned that if you, so let me just to demonstrate again. It actually doesn't start the timer until you click in. So once you click in, there we go. Now what should happen if our hypothesis is correct is every 10 seconds, that function is going to be called, and yep, there it goes. Now, because we have a score of 0, we should see this function basically return 0, because what's going to happen is if we go back here, we can see our flag is set to -4 again. Our param3 is set to -2. Now we should be able to see that when this function is called, because our score is already 0, we shouldn't have it set below 0 here. So let's go see if that's accurate. So we get to the point where let me step back here. We're checking the score mode against 130. It's not 130, which means it's not none. So we skip that part. And now we're at this point right here. We're comparing the flag. If I highlight that line, you can see it in Ghidra as well. Same command we're seeing over here. We are checking the flag to see if it's -4. And it is, so we're going to take this jump. And by the way, the debugger will tell you that the jump is about to be taken right here. And now we should be seeing that function that sets it to 0 if it's negative coming up now. And what we should see is in this function, we've been passed -2 as param 1. So this is -2, so that's set to 0. Here's the comparison to check it against 0. The jump is not taken, so that means it's not going to skip this line. So we should see next, it's going to change the value from -2 to 0. And it does, just as we hypothesized. So what does confirming that little hypothesis do for us? Well, now we know that this is not just any data address. This was the value -2, and it was being added to our score. Our total score was being checked against the value 0, and if it was less than 0, it was being set to 0. So now we know this is not just data address, but score address. And take note that it's actually, maybe a better label would be score base address, because, or maybe something like score address minus 0x30, because we're actually adding 0x30 every time to that address. So keep that in mind. So now that we know that that's where the score address is being held, let's try to manipulate the score just to make sure we have a base. Here we go. So now our score should increase by, what was it? Oh, it's actually after we flip it. So let's go ahead and flip it. Now it should increase by 5, I think. Yeah, so we have a score of 5. And the next time we hit that function, which should be in every 10 seconds, there we go. We know that this 71C88 is our score address -30. So let's go ahead and type that in to the dump view to look at it. But let's add 30 to it, so that'll bring us to, sorry, my hex math. I just want to be sure that I'm doing this correctly. So if we take 71C788 plus 30 hex, 71C7B8. Should have known that. And there we see, indeed, there is a 5. And this is in Little Endian. So keep in mind that these 4 bytes are all part of the score. It's just read from right to left. So now what's going to happen is, since we hit 10 seconds, we're going to lose 2 of those points. But now in our debugger, we can manipulate our score by going to binary edit, and let's make it something ridiculous like, well, let's take it to the max value we saw before, or here, I get to edit all the values here. Let's set it to the max value it can be before it goes negative, which is FF7F. And again, remember, this is in Little Endian, so actually in the calculator it looks like this, 7FFFFFF, which is 2 million and some change. And the reason that is the highest value you can get is because, again, this is the highest decimal value we can get with all the bits set except for the last one. So when we change that, let's put OK, play, and look at that. Now we know exactly how to manipulate our score. So now that we know where the score is actually held in the program, and we know how to edit it, that's awesome. But we still have a couple of outlying problems here. Namely, every 10 seconds, even though we have a super large score now, it's still going to go down by 2 points because of the way the solitaire timer rules work. Now, the timer problem might actually be the easier one to solve right now, because if you noticed while we were looking at these 4 bytes which hold our score, if I run the program, right next to the score, we see these 4 bytes which increment every second. So maybe that is indeed our timer. If we wanted to check that, what we can do in the debugger is set a breakpoint. We're going to do a hardware breakpoint on a write to the byte. Now, the reason I'm using a hardware breakpoint is because the memory breakpoints they have here don't allow you to get down to the byte level of manipulation. And I just want to see I just want to breakpoint when this particular byte is written to. So basically when it's changed. So I'm going to set that. We'll hit run, and it's changed. It's showing me this line, but it's actually the line before where that change is made. So let's go hop over to Ghidra and see exactly what's going on in the function at 10051C1. Let's pull this up. So this is the line that it was breaking on. And over here in the decompile, oops, I didn't mean to drag that whole thing over. We can see that there is a value being assigned to some array in memory, which is what we were looking at in the debugger. We don't really care what the value is as long as we know that it's being assigned whatever this is. And what this is calculated right above there by this function. Let's take a look at this function. Well, this looks familiar. This is just like the other function we saw. In fact, is it the same function from here? 23b5, we should have labeled it, I guess. We'll say checks against 0. But I don't think it's the same function, although the code is very much the same. Yeah, so it's a different address, but very similar function. It checks the numbers, and if param2 is less than or equal to param1 gets set to that value. Except instead of 0 in this case, it's checking it against 7FFE. And the value being checked is whatever this is plus 1. What does all that mean? Well, let's take a look at on the calculator at what 7FFE is equal to. It's equal to every bit set except for the first one, which again would flip us over to negative, and the last one. So what this is saying is if this value plus 1 is greater than 7FEE, then we want to keep it at 7FFE. Sorry, what did I say? I think I messed that up the first time. 7FFE, yep. Why would we want to do that? Well, if this value plus 1, we'll add 1, is a greater than or equal to 7FFE, if the next time we get here and we add another 1, it's going to overflow and become negative. So what this is doing is basically preventing the timer from overflowing. So if you play so long that you get to the point that you've played for 32,767 seconds, which that's about 9 hours. If you played solitaire for 9 hours, your timer will stop just short of going into an overflow and becoming negative again. So it'll stop at 7, sorry about that, there we go, 7FFE, which is 32,000 something seconds. So we know with certainty now that this, whatever this value is here, is indeed our timer. Now the question is, how do we stop it from being incremented over and over and over again? So there's a couple ways we could approach trying to disable the timer completely. For one, we could look at the instruction right here that loads that new timer value in. And we could set this to, instead of a move instruction, to load 0 into that address. But honestly, the easier approach here is just to get rid of this instruction altogether. And the reason we can do that is because there isn't any impact downstream. And what I mean by that is sometimes when you patch over, if you just remove instructions, it can be a little dangerous because let's say you remove an instruction that sets a memory address that is then used down below. In a very specific context. If you remove that instruction, you may crash the program. But now that we have a good understanding that this register or this address in memory is just going to have the timer value, removing this instruction that moves that new value into it, it's not going to have all that big of an impact. So what we can do is right-click, patch instruction, and just change this to a NOP, which means no operation. And then we can get rid of every other operand because NOP has no operands. Hit enter. And you'll still see, once again, it messes with the listing a little bit because now we have these 2 stray bytes. Where do those come from? Well, if you look here, those were the operands we set before. So what we can do when Ghidra patches over those, what we can do instead is, well, I guess I have to go back and patch it one more time. Let's get rid of these. We can just go ahead and open back up our bytes view and set those to also NOP. So I can do that by clicking my pencil. And the opcode for NOP, as you can see there, is 90 in hex. So we just add 2 more 90s, and what that will do is set 3 NOP commands to fill all those bytes, basically. So now, when we write our new Solitaire version, that timer should not increment. In fact, let's go ahead, well, actually, let's wait to test that, because the other problem we need to address still is the scoring situation. How do we manipulate the score so that every time we score, we get some random, large value, arbitrary large value in score instead of just 5 points? Well, to do that, let's go back to our decompilation view and let's go back to our function we were looking at that was manipulating the score right here. So now we know that this param3, which is added to our score address, is score from, what should we call it? We should call it standard score, I guess. Or maybe I would just put default score value, because I don't want to use standard because that indicates a specific scoring style. So we'll say default score value, because depending on what score mode we're in, the score value is going to change a little bit each time. So also I can get rid of my hardware breakpoint now and just let this run. Now what we need to do is figure out where this score value is actually being pulled from. So we know that it comes from param3 here. That param3 in turn is provided by the parent function, which is going to be, where am I, right here? It's going to be this guy right here. So this is my, what I call it, default score value or something like that. And this function here is actually called from 6 different places. So that could get a little dicey trying to figure out where exactly that parameter is going to come from. But we can see in the debugger that we're being called from 100517A specifically when the score is being modified, which equates to right here. Now you may be wondering, why does this say 5175? This says 517A. It's because in the debugger, this is a return address. So this is pointing to the command that follows right after the function call, which is 517A. 5175 is where the function was actually called. So let's bump open Ghidra here, and we can see that we were called from this guy right here, and uvar1 right here is going to contain our default score value. Okay, so where is that set? Depending on, it looks like there's a few if-else statements here. So again, we're checking the score mode. This can come from a few places. So the last place that default score values is assigned is right here in this line above, where it's assigned to puvar2's value plus param2 times 4. So whatever puvar2 is probably the base address of wherever our scores come from. And if we highlight it, it's a very, I thought I set the highlight, I did set the highlight on it. It's very, let's try to get a darker highlight. There we go. There's only 2 places where puvar2 gets its value, and it's right here and right here. 2 different predefined data regions in the executable. And take a look at what the difference here is. So if score mode is standard, if you remember that's the code for standard, puvar2 comes from here. If the score mode is none, so if it's not equal to Vegas, which is this guy right here, this just returns. But if it is equal to Vegas scoring, it comes from here. So now, since we're in standard scoring, Let's click on here. It takes us to this guy right here, which is a long list of values. What is this thing? Well, take a look back here and how this is written. So pu var2 plus whatever the second parameter is times 4. This is an index, basically. So you may be wondering why it's multiplied by 4. Well, if you look at, let's go back to that table. This table here, it doesn't look like it right now, but each one of these values is actually 4 bytes. So param2 times 4 is going to take us to the next value in that table. Now, how do I know that about the 4-byte thing? Well, let's take a look at what happens when we select this whole value at data 1007034. Right click, data, and we're going to select D word, which is the equivalent of 4 bytes. Take a look at what these values become, and they might look a little familiar. This first one, FFFFFE, if you remember, is -2. Let's pop open our calculator just to check our work. FFFFFFE, negative, oops, I need to change this to D word though, -2. Let's try FFFFFFEC, oops, too many F's, -20. A is simply 10, 5, 5, and then FFFFFF1, -15. Do these sound familiar? They should, because if you remember, these are exactly, let me get the tab open here, sorry. I'm building so much suspense right now. If we look at the standard scoring system, these are exactly the values we'd expect to see. -2 for every 10 seconds elapsed, -15 for points moved from a suit stack to a row stack, -20 for each pass through the deck, and then 5 points for a card turned face up, 5 points for each card moved to deck to row stack, 10 points for each card moved to a suit stack. This right here is our scoring table for standard scoring. And now that we know that, we can manipulate these values. And by the way, this other one that was referenced, again, remember this is only set to PD var2 if the mode is in Vegas mode. So keep in mind that that is the Vegas scoring table if you're playing Vegas style. Oops, I did a comment again. I meant to do a label. And we can also go ahead and tell Ghidra that these are all actually, oops, I don't want to highlight too much there. There we go. These are all D words as well. So now if we wanted to, we can now say, let's have no negative scoring. So let's patch this data. And let's just set this, actually let's do this in the byte view. It will probably be easier and cause fewer problems if we just edit the bytes directly. Let's get rid of all these negative values. We don't like negative values. So let's say here, we will just set all these to 0. And instead of just adding 10 points, let's add whatever the highest was we had, which was FFFFFF7F, which is like that 2 million number. And let's just do that for everything. So no more 5 points per card or whatever. Oops, 7F. It's always going to be maximum points every time. Now the one value we don't see here actually, which you may have noticed if you're paying very close attention, is we don't see -100, which is interesting. Why don't we see that anywhere? Sorry, oh, there we go. I just had to enter there. My mouse froze up on me there. And, oh no, yeah, it changed them. Okay, perfect. So we don't see -100 here. Why is that? Well, let's see what -100 ends up being in this. It's FFFFFF9C. If we search for that value, I guess I don't have to do a hex here. I can just do -100 and it should understand what I'm looking for here. And if we look back at that last, oops, let me go back to my decompiler view. If we go back to that last function we were looking at, we actually see negative 100 is right here. Why they decided to define it there rather than the scoring table, I'm not sure. Maybe just because it only shows up in standard mode, they didn't, well, I'm not sure actually. Could be a multitude of reasons why it ends up here and not in the scoring table. But in case you were wondering, that's where the negative 100 comes from, is there. So now we've manipulated the standard scoring table to only give us max points every time. Now the last thing we need to do, now that we've changed the timer value and the scoring value, is we need to save away our new binary. So let's go ahead and kill our debugging session. It served us very well. Also, one thing I haven't been doing that I should probably be doing for best practices, I haven't been saving my Ghidra database. And I also didn't check to see if autosave was on. So make sure you are saving often. Okay, I thought there was an autosave feature. Maybe there is, but I'm just not seeing it right now. So let's go ahead and export our program. And again, we'll just call this this time let's call it like God mode, because we've just taken the fun completely out of it by manipulating the score like that. And let's run it. So first thing you may notice, our timer is not moving at all, which is exactly what we intended. Next thing, let's try to get a score here. Gosh, if I get any good cards. There we go, I'll take it. Immediately 2 million points. And if we do this again, we might actually trigger an overflow. Oh, cool. So it kind of messed with the graphics here. But what is cool is that when we went over our score, and remember, we overflowed it, so we're in the negative numbers now. That function kicked in and kicked us back to 0. So one thing you might do if you experiment with this is maybe change the score enough that it's a high enough number that you get a ton of points, but it's not so high that every time you score, you just overflow it over and over and over again. But congratulations, you just cheated your way at a 30-year-old game, probably older game now actually. But hey, it feels really good. We did so much good reversing there. We had a lot of good hypotheses that we were able to develop right out of the assembly. And we were able to confirm those through the debugger and through manipulating things in the game. And now we have a cool hacked version of Solitaire. So before we move out of Ghidra and into some other tools, one last thing I wanted to come back to from the very beginning of the video are these weird strings we looked at. And there's a really cool site called the Cutting Room Floor, I'll put this link in the description, that talks about some of these weird strings we found. And what they say about these 3 strings in particular are these first 2 ones are kind of leftovers. Nobody really knows what the heck I don't know message was about, which is really interesting. And I think initially it actually said hell, I don't know. Yeah, right here in NT4, which is interesting. And then this one, I don't think it actually works. I think they said it was the second one, the functionality of the second one has been removed in the retail, so it just seems to freeze the game. But force a win. For those of you who are real ones, you probably remember that there is a cheat code built into Solitaire to force a win, and it is simply pressing Alt-Shift-2. And that's what we saw in reference to that force a win. In fact, let's try it right here. Alt-Shift-2, we automatically trigger a win. The last little hack I want to do with the game itself, the gameplay, is what if we wanted to change that cheat code to some other keyboard combination to make it easier? Like, let's just say we want to make it the letter W, for example. Well, let's go back to Ghidra and check out that string again, and we may find a way to do that. So if we go back to the string table, we see that force a win has a resource string ID of 1010. So let's search for that and see if it shows up anywhere. It shows up in exactly 1 space. Let's go to the decompile view, and hey, this looks very familiar. We saw this section earlier, so it seems to say if uvar3 is not that value, then run that ShellAbout W command and pop up the dialog. So what if it is that value? We don't really see another section, but we do see that uvar3 is determined by this param3 blah 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 blah. It's not immediately obvious what that variable is being used for. So let's try one other thing before we dig in here and try to explore and backtrack here. Let's try a whole program search for, again, that value. So there's nothing more in the program text. There is one more place we haven't talked about where you should probably do searches if you're looking for a specific value. That might be an ID or something that shows up in a structure in the code, and that is a memory search. So let's go to memory and search for the value 3F2 and search everything. Make sure you don't have search selection selected. And now we actually find that value one other place in the resource section. And it's in this resource called an accelerator, and it's named hidden accelerator. Interesting. So let's see what's going on here. By the way, that value shows up right here in this little table or array looking thing here. So what's an accelerator? So looking at the Microsoft documentation, we find out that accelerators are closely related to menus and they rely on keystrokes. They're almost like shortcuts, keyboard shortcuts. They are made up of an accelerator table consisting of Excel structures, which we'll look at in just a second. And that structure contains the accelerator's keystroke combination, the accelerator's identifier, and various flags. So let's take a deeper look at that. So if this is our, let me do a side by side here again. This is our accelerator structure right here. The first byte defines the accelerator behavior. This member can be one or more of the following values. It can be pressing the Alt key, pressing the Control key. No invert simply says that no top level menu item is highlighted when accelerator is used. So basically that should be set to none in the case of the cheat code, because if I go back to there we go. If I run my game again and I hit my keystroke, nothing pops up. It just runs the cheat code and that's it. So that should be set to nothing, and then the shift key must be pressed, and the last thing is just a true or false, which equates to 0 or 1, specifying that the key part of this is a virtual key code. What the heck is a virtual key code, which is stored in the next word? Well, it's a hexadecimal value that represents a keyboard key. So using what we know about the shortcut, we know it's Alt-Shift plus the number 2 on the keyboard. Well, let's look at what the number 2's key code value is in this table. Let me just scroll down, actually, probably easier than searching. It is hex 32, which we indeed see right there. And what was the other part? So the Alt-Shift. So in order for the Alt-Shift to be set, we're combining a few of these flags. So remember, Alt is represented by hex 10. So let's put that in our calculator. The reason I'm doing this in the calculator is when you see these values that combine multiple, or that can be multiple values added on top of each other, you'll notice that they're staggered by bit. So you'll see that the Alt one is hex 10, which is this 5th bit right here. Control is 8, which is the 4th one. No invert is 2, which is the 2nd one there. Shift is the 4, which is this guy here. And the vert key, like I said, it's represented true. It says true and false, but it's 1 and 0, 1 for true, 0 for false. That's this place. The reason it's designed that way as a flag is because you can layer them because they don't have overlapping bits. So if I want to say that I press Alt and Shift, I bitwise or 10 and 4, I get 14. But that's not what we see here. We also see 17. Well, that's because we want to specify no invert because no highlighting is done. So we'll specify or that with 0, 2. that gets us to 16. And then the 1 comes from fvert key being true. So if we OR that with 1, we get 17. So to backtrack and review that, what that means, that 17 hex comes from layering all 4 of these flags, vert key, shift, no invert, and alt, with each other. And when I say layer, all I mean is those flag values get ORed, bitwise ORed with each other, which means that all their individual bits get set, basically. So you can see that the alt bit is set, the no invert bit is set, the shift bit is set, and the 1 bit is set. So we basically confirmed that we're looking at an Excel structure. We have the fvert member here, we have the key code character for 2 here, and we have the ID here. Now, one thing you might notice is a little odd is this is supposed to be a single byte. Okay, we see that's a single byte represented by a single hex, or 2 hex digits, I should say. But then the key is supposed to be 2 bytes long. So what's going on here? Because in theory, we should see fvert, a single byte, followed immediately by 32, 0. Why is there an extra 0 added right here? Well, the reason for that comes from the idea of structure padding. And this is just an optimization that you should definitely know about as a reverser, because it might throw off some of your mental alignment of some of these things. All that structure padding means is that the compiler sometimes adds an extra empty byte in between these if they're not an even number, if they don't align to the architecture of the computer you're programming on, just so everything stays in alignment. And I'll post this link in the description of the video because it has a good description of why we need structure padding and what happens when we try to access things that aren't aligned. But I'll leave that as an exercise for you to do to figure it out. All you really need to know, though, the TLDR, is that structure padding might introduce these null bytes that don't necessarily show up in the documentation, just to keep things all aligned. The other thing you might have noticed is that there's actually a second accelerator defined in here, and it actually has a 8.1 value. Where does that come from? Well, it's actually not listed for some reason. It might be it's just legacy, but it's not listed in this article, but a separate article called Excel Table Entry Structure on MSDN. And the 80 hex says simply that this entry is the last one in an accelerator table. So that's why that bit is set to 8, and then the only other flag that's set is the fvert key to true. And the f virtual key is 7.1 hex, which is right here. It's the f2 key, and the ID is 3E8. So what is that accelerator? Well, let's go find out. Let's search for 3E8. And we see it come up a few places, but what will give us a hint is looking at this match right here in the resource table. It's also mapped to an ID called, or I should say, that is mapped to the deal function, which also has F2 specified right there. So that other F2 accelerator is just the accelerator to deal. So you just hit F2, there's no need to hit Shift or Alt, and it will deal the cards. That's what that other accelerator is. So back to the task of changing our hotkey to be something simple, like let's just make it the letter W. So for W, the key code is 57. So to put our new cheat code in, we'll change this. Oh, I did it again. I need to use the byte view. We'll change from 32 to 57 hex. Need to make sure I put myself in edit mode first and type the right things. And the first byte is 17. We can just leave that as 01 because the rest of the options really don't matter all that much. We just need to leave 01 in there to tell it that it's a virtual key code. So let's export our newly patched program. We'll save it as the same God mode exe. I do need to make sure I closed. Okay, yeah, I closed my session. And we will hit OK. overwrite. All right, and let's see if we actually implemented the cheat code correctly. If we hit W, instant win. So congratulations on making it through the bulk of the video, the hardest part for sure, which was actually reversing and modifying the gameplay to cheat and increase our score, stop our timer, change the cheat code for the instant win. Now we're going to do some more fun stuff outside of the disassembler and debugger. What we're first going to do is modify the Solitaire program to use our own card faces and card backings that we can set ourselves. And I'll give you a little script that you can use to generate those. And then the next thing we're going to do to wrap up this video is to weaponize the Solitaire executable. And what I mean by that is we're going to introduce our own potentially malicious, hopefully not actually malicious, but more of a, good-natured malicious prank into the code so that we can play tricks on someone who might be playing it, or just run something custom every time the game is run. So let's start with modifying the actual card backings and fronts. We can do that. Let me just minimize a lot of this stuff, close out of here. We don't need the debugger anymore. Let's now shift gears and open up a new tool called Resource Hacker. And I'll leave a link in the description to download this. It's a neat little tool. If we bring in just our Solitaire executable, we can look at all its resources, like the things we looked at in Ghidra, like the dialog box stuff, the string table that has all the strings we were modifying. You can even see the accelerator, and the cool thing is Resource Hacker actually translates all those values. So all the stuff we figured out manually, which it was good learning exercise to do that, Resource Hacker will just show you those flags and what they mean. We also see those icons we saw. We also see some menu items that we looked at very briefly. But yeah, Resource Hacker is a wonderful tool to look at resources in a very quick and lightweight manner. But the cool thing about this tool is you can actually also swap resources. So one thing we didn't circle back to yet is the fact that when I tried to save my modified program outside of this folder, it would not run because it couldn't find this library. And we saw in Ghidra that Solitaire imports certain functions from cards.dll. Well, the other thing it needs cards.dll for are the actual card faces themselves. They are listed in this library. And the reason cards.dll is a shared dynamic library is because when we had Spider Solitaire in there, it's also going to load these from cards.dll. So the programmers basically exported all the card backings and all the card functionality to its own library to be used in all sorts of games, which is very clever. Now, as we scroll through here, you'll also see all the card backings. So here's where we can get really fun with our mods here. We can actually swap out any one of these for our own picture. We can make something in MS Paint, or I'll show you another couple ways we could do some interesting mods. So let's start with this guy, actually the froggy. Let's say we want to make our own custom backing. Like I said, you could open up MS Paint and this shows you the size of the image. It's 71 by 96. This is a bit depth value of 24 in mode RGB with red, green, blue. You really don't need to know all that stuff unless your program you're making it the art in needs to know it. All you really need is the size. So what I'm going to do is I'm actually going to pull up a, there we go, online photo editor called Pixlr. And I'm going to make my own card backing. And I have an image in mind that I will pull in here. Let's see if I can drag and drop. I have to find where I put it. Beautiful. All right. So let's go ahead and resize that to, what was it? 71 by, get out of here, taskbar. 71 by 96. Also, I think I accidentally dragged this over. 71 by 96. So let's go to set page size 71, 96, and apply. Oh, I didn't expect that. Okay, that's not what I was going for, but that is kind of perfect. Okay, I really just wanted to do something like this. Either one would work just fine. Oh my god, I was not ready for that, especially not this late into the day. All right, let's center him. Beautiful, Nick. All right, there's our card backing. Again, you can do whatever you like. Now, they don't have a BMP option, which is the format that I want to save mine in, but let's save it as PNG. And what I'll do is I'll just open up Paint and I'll drag my card in there and I'll just resave it as a BMP style. And let's go ahead and save that into here. And I'll just call it Nick. Beautiful. All right, let us exit out of there. And now back in Resource Hacker, what we can do is go to Action and Replace, or you can do Control R, or you can right click and hit Replace. And we will open it. It keeps going to my testing folder there with Nick and Replace. Oh yeah, so let's just save that. Go back to our game. We're gonna have to reload it. Get back to our Solitaire folder and back in here. I'll just run the original one. Oh yeah, that's looking great. Now for the card fronts, I'm actually going to give you a resource. I thought about going through and writing it from scratch with you all in the video, but we have so much else that we've covered and will cover that it didn't make sense to spend so much time on this script because it's just kind of a little extra. What this Python script does is it generates a list of cards that you can use to customize things like you saw in the thumbnail for this video where I put my name, and I'll run it here and show you what that looks like. So the Python file uses Pillow, a Python library, to basically draw these card images using the right card width and card height, and it defines out the suits and what symbols they should use and the colors they should use. And then at the very bottom, it'll write a couple files to become what's called a resource file, a .rc file here. And I'll show you how this will work. I have it in the comments as well, but I'll show you how this will work to actually get Resource Hacker to ingest card images in bulk. So, for example, for the thumbnail for the video, I replaced a bunch of cards with the strings Jeff of all trades. And right here, if you modify the script yourself, you can put in your own text. You can assign different card values to what those texts should be. So there should be one card value per character here. And then the suits I've left blank. And what that will do by default is just cycle through and randomize the suit just one by one by one. But you can also put one suit per character. And what will happen when you run it is, let me get to that folder real quick. It will spit out all these custom card images with whatever characters you gave in the text. So we can see we have D, E, all the characters in Jeff of all trades in different suits. Looking really good. The other thing the Python script does is it builds this cards.rc file. Now this resource file maps each of these cards to a particular ID, and that ID goes right in alignment with these IDs you see right here. So 1, 2, 3, 4. So meaning this RC file is saying the J card of the club suit will be assigned to ID 1. So we should see the J end up here. We should see the E end up in 14 to take over the Ace of Diamonds, etc., etc. Now, before you can actually import this into Resource Hacker, there is one extra step, and I've included this in the comments for what needs to happen here, and in the GitHub repo there's full instructions that will walk you through this. You need to run the command to actually compile cards.rc into what's called a resource file. And it's as simple as windres cards.rc tac-o cards.res. There is another command if you're not using windres that you can use with the rc.exe executable provided by Microsoft. That's also in the GitHub repo, how to use that. So once I have my resource file though, I can go to Resource Hacker, and instead of right-clicking individuals, I can go up here to Action, and I can say Add from Resource File. And I can select, let me find the resource file I used, and it's going to pop up the screen. I'm going to select each and every one of them, and I'm going to tell it to overwrite any existing bitmaps, import, and it will show me which ones have changed. And sure enough, J is mapped to that one, D is mapped to that one, and we see them line up exactly as we imagined. So now I can play with all my, once I save this, we'll start a new solitaire session, and we'll play with our custom cards. Now it is difficult because I don't know what values all of these are, but that's just an example of how you might be able to use that for a prank or actually design your own card art to use with XP Solitaire. You could build up some pretty cool mods with that. All right, so if you stuck around this long, we have hacked and modded the heck out of this game. We no longer have a timer. We have ridiculous scoring set on our game. We've changed the images and created custom card fronts and learned how to replace resources. There is only one last goal we have to accomplish, and that is to actually do the weaponizing part of this video. Now, when I say weaponizing, I want to add some asterisks here. What I'm going to show you is a technique to add your own code that will run when you start the solitaire game. I'm going to be using some nerfed code, meaning it's not going to do anything truly malicious, and I'll just say that I do not encourage anyone to do any kind of damaging of anyone else's machine that they don't have purview over. If you want to write your own malicious code and test something, please do that in your own sandboxed environment that's only going to impact your stuff. Please do not use your knowledge and skills for evil. Use them for good. With all that out of the way, let's talk about the technique we're going to use to weaponize solitaire, which is called DLL hijacking. And it goes back to what I was saying about the necessity of having cards.dll packaged along with solitaire. Now you'll notice also, in case you're wondering why there's two here now, Resource Hacker, when we replaced the images, it created a backup of the original, which is kind of nice. So we'll leave that there for now. What is DLL hijacking? Well, it's a method of injecting malicious code into an application by exploiting the way some Windows applications search and load dynamic link libraries. So this article, again, this is another one I'll post in the video description. It goes into this technique a lot in depth. And there's a specific type of DLL hijacking. I don't know, some people use this synonymously. I'm going to use it kind of as a sub-technique of hijacking. And that's called DLL proxying. So the idea is that we find out, again, we could do this from Ghidra, we find out which functions Solitaire is using from this cards.dll library, and then we write our own code that will forward on most of the functions, but when one of these is called, we will swap out its code with our own code and then forward on the rest of the call to the original function. So basically we're sliding our code in so that it just runs our code and then passes through everything else as if our new code is not even there. To do that, there are a few prerequisites. Number one, this only works because we know cards is located in the same directory as solitaire, and we kind of know that it's always going to be packaged together that way. It might get a little trickier if cards was located somewhere else on the machine. The other thing that's working in our favor is we now have 2 copies of the DLL here, and we're going to need that because we need one copy that has our own malicious code in it, and we need the original copy because we need to forward all of the function calls to that original copy here. So we're actually going to end up keeping both of these DLLs that Resource Hacker just happened to generate for us. So in order to actually build the weaponized code and build this DLL, we're going to need a few new tools. One of them is, I recommend, and you don't have to download these exact tools, you can use whatever is suitable for your operating system. So if you have Linux and a Linux operating system, You might have G++ or GCC installed already. That's the compiler we're going to use. Otherwise, if you're on Windows and you need it, I would recommend downloading MSys2 because it's super simple to download G++ and our GCC compiler with that. So assuming you did that, I will walk you through what that looks like. So I've got MSys installed. I will go ahead and open up a terminal. And MSys is basically like having a little mini Linux terminal for your Windows machine. It also has a lot of tooling and libraries installed with it. And it has a package manager called Pacman. And the first thing we need to do, and this will probably not work for me because I have it installed already, but you'll run a command, and all of these commands and these instructions are in the GitHub repo for this video, to install GCC, the new C compiler. And so it's saying, okay, we'll go ahead and install it again, even though I'm pretty sure I have it already. We'll go ahead and install it. So this gets us the compiler we'll use to compile our code. Again, you don't have to do this if you want to use something like Visual Studio to compile your code. This is just what I'm going to use for the video because it's a pretty simple process. I'm also going to download the 32-bit and 64-bit tool chains. Those are going to add some additional tooling for our compiler. There we go. And libraries. There's nothing to do for me because they're installed. But again, if you need those commands, they'll be in the GitHub repo. So now that we have our compiler set up, I can close out of there because I'm going to use Visual Studio Code to actually go in and run these commands. And the first thing we need to do to set up is get familiar with cards.dll and choose a function to run our malicious code in. So this website, again, I'll include it in the description. It actually has a very nice description of all these functions in cards.dll. If you didn't have this nice website, you'd have to go into Ghidra and you could actually open up cards.dll in Ghidra. In fact, let's go ahead and do that while we're here. We'll just go ahead and add cards.dll, the original one, to our project here and open it up. So we could go through and manually derive all the information about these functions, but the truth is, by definition, a DLL proxying attack doesn't need to know much about the original legitimate DLL. We're going to basically take any calls to our malicious code and pass them right through. We don't really care about how these functions work, but there are a couple pieces of info we do need to know. And one is, when is the function called? Is it called, first of all? When is it called and how often is it called? And are there any other side effects that we need to worry about? So that would be the only reason you'd need to go in and dig a little bit and see, when is this called? When might it be called by Solitaire? You'd have to bounce back and forth between this listing and the Solitaire listing to figure out how often these functions, I actually went imports, are called. So like the draw function is probably going to be called every single time or every single frame of the game because it has to draw a card every frame of the game. But the CDT init might be one that we look at and it's only called once at the very start of the file, and that is it. Now, again, you could use Ghidra to get that information, but because this nice website exists, we know for a fact that CDT init is indeed only called one time at the start of the application. These other ones are going to be drawn or are going to be called multiple times, like CDT draw. The other nice thing the website gives us is the function signatures, or what they're called. So it tells us what the return value is, the type of function, and the parameters, which we could also get those mostly from Ghidra. The only ones, not in here, but in the cards.dll, the only part of the function definition we may not get are the types of parameters. So you see here, it's just got an undefined versus on the website, it tells us exactly that it's an integer. But you could derive that information from looking at the context. And you could also see that it returns a Boolean because we can see it only returns a 1 or a 0 value indicating a false or a true. Again, you could do that, or you could take your best guess and experiment around and brute force it, or you could use the nice website that already exists for this particular case. But that's not going to happen often, I don't think. So let's say we've gone ahead and done it. We've selected CDT init as our proxied function that we're going to write with our weaponized code, the next thing we need to do here, let's start a new file, is we need to make what's called a definitions file. And I do have a link I can post on this as well. Def files are basically describing various attributes of the DLL. For our purposes, what we're going to use our def file for is specifying which functions we're going to forward to the original cards.dll. So let's go ahead and call this something like say cards.def. And the format of this def file is pretty simple. We're going to top it with exports as a kind of prefix, and then the next few lines are going to be the names of all the functions except for cdt init, because these are the ones we want to pass through to the original DLL. Oops, it should be a dot cdt draw at 3. So let's talk about this line here. What this is saying is the cdt draw, if my library, the malicious library, gets sent a function call for cdt draw, just immediately forward it to cards.original.dll, which is the original legitimate DLL, to the function within that DLL called cdt.draw. And this last bit here is what's called an ordinal. And it's an @ symbol followed by a number, and the number is the ordinal of that function. Ordinal meaning just a alias for that function. So basically, this function has an alias of 3, or number 3 in the DLL. Don't need to really get into the details of ordinals, but just know that you can derive that right out of Ghidra by looking at cards original DLL, and at the very top of each function definition, you'll see this little pink line here that says the ordinal number. So cdt init has an ordinal of 1, cdt draw has an ordinal of 3, draw ext has an ordinal of 4, and the rest of them in turn. So with that knowledge in mind, I'm just going to copy paste over the rest of these because they all follow the same format. So again, we don't include cdt init because we're going to actually rewrite that function from scratch to include our malicious code. But this is our definitions file. We'll just save that to the side for now. The next step is to actually build the C++ code that's going to have our quote-unquote malicious code in it, and that is going to proxy the cdt init function. So we'll write this one from scratch, and the way to do this is to start out with some libraries we're going to import. So we'll include IOStream, which is input output. We'll just need one thing from there. We'll include the windows.h header. And I'm also going to do what's called a define statement here. And you don't need to have a deep understanding of C++ to write these things. I'm not going to go too deep in the weeds. But this define keyword is just saying I'm going to define a little shortcut, or a little keyword shortcut. So my keyword is extern DLL export, and it's going to be a shortcut for everything that comes after right here. And this line is going to look really confusing. All you really need to know about this right here is it is a signature that we place ahead of DLL functions to mark them as exportable. And what I'm doing with the define statement here is I'm saying instead of writing this out every time for every function, I want to just condense that into one word, which is extern DLL export. That's all that is. It's just aliasing all of this into one little word there, keyword there. The next thing we're going to do is use a type def statement, which is somewhat similar to what we just did with the keyword there, except this time we're going to write out the function signature of the function we want to proxy. So that's cdt init. And it looks something like this. I can't believe I just did that. I read with, and I said this, and I said this. Oh, that's embarrassing, but it has been several hours that I've been recording now. All right, so it looks like this. And I want to pull this up side by side with that website I had up earlier so you can see what we're doing here. So I took the signature of the original function And I've done what's called a type def. And I've basically said, hey, I'm going to be taking a reference to a function that looks like this. And I want you to know, compiler, that when I refer to cdt init pointer, like this word right here, what I mean is you should prepare to call a function that returns a bool that is of type WhenAPI and that has these parameters and these types. That's all I'm doing here. So this cdt init pointer becomes almost like a keyword or a substitute, an alias for the function that we're going to proxy in the original DLL. And I'll show you how that's used in just a moment. The next thing we're going to do is use that keyword we just defined up there to define a API entry function called DLL main. And this has a standard set of parameters that we'll put in here. This is all available, by the way. All the stuff that I'm putting in here is in the Microsoft documentation. It's actually one that I don't have pulled up, but if you search API entry DLL, there we go. There's actually a tutorials point guide that's probably a little nicer than the Microsoft documentation that shows you how to write a basic skeleton for DLL. And it probably will do a better job of explaining it than I am. So I'm going to add this to my list of links to include for you all in the video description. But suffice to say, this is a boilerplate skeleton function that when our DLL is loaded into the program, it's going to run this function first. It's basically going to look for that reason to call, and typically you would have different actions for the different signals that were put here, like DLL process attached. So when our DLL is attached to a process, do X, Y, or Z. When our DLL is attached to a thread, do X, Y, Z. However, we don't need our DLL to do anything except for account for one proxied function. So we can just leave all of these cases blank. And what's going to happen is no matter what, whatever loads our DLL, we're just going to return true, no matter what. Because we don't care if someone loads our DLL, we don't have any extra actions we need to take. We just let it go and return true and say, hey, everything's good, I'm loaded in. Now the next part is the most important part for our purposes. What we want to do now is create our own version of cdt init that looks exactly like the original one, because we want the user program to not know the difference between our DLL function and the original. But instead of just calling the original function code, what we're going to try to do is get a loaded copy using load library of the original cards.dll, which on my machine is now renamed to cards_original.dll. And since it's in the same folder, I don't need to put a prefix, but if you had it somewhere else, you might put, C/user, blah, 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 blah. But since it's in the same folder, and it really should be in the same folder for our purposes, we'll just say cards_original.dll. And if that fails for some reason, so we can do that by doing if not loaded DLL. So if this for some reason failed, we're just going to print an error message like, this is just the default one that I found with an example, and we'll put the error code here, get last error. So that's just going to print an error code if for some reason we can't load the original DLL. If we accidentally renamed it, or if it's not in the same folder, we'll print that error message and we'll return false and nothing else will happen. So after we load the library, we want to load the specific function, so the cdt init, from that library. So this is our original function, and I'm going to call it, let's call it proxied function. And I'm using that cdt init pointer value that I type defed up here to tell the compiler what kind of function that I'm reading out of this DLL. So I use get process address loaded DLL. I'm passing in the DLL I want to load from, and then the next argument is the name of the function I want to load from that DLL, just like that. Oops, except it's not get process address, it's get proc address. Let's see if it likes that. Yep, there we go. And one more time, I want to make sure that if that for some reason failed, that proxied function is going to be set to a null value. So I want to just return false if for some reason I didn't get a good function back. Hopefully that doesn't happen. It shouldn't happen. So that's our proxied function. Next, we can finally start putting in our weaponized code. So this is the code that we're going to run. Added too many stars there. And I'll just make a comment section here that shows where the start and end of our code will be. But I'm not going to write it quite yet. Did it again. I'm going to finish up the rest of the function so you can see how the rest of the proxy is going to work. So after our malicious code runs, we're going to take the actual function we're proxying, proxied function here, which again, this is just an alias to the original CDT init function in cards.dll. We're going to send it the width and height that we received from the user, and we're just going to pass it forward like nothing happened. We're going to run our code, pass the proxied function what the user passed into us. We're going to save the result off into a Boolean cold result, and we're going to return that to the user. And it's to the user, it's like nothing, has occurred. They have no idea that their function actually ran some other code along with the original CDT init code. Now, one last thing I'm going to put in here is the free library call. Anytime we call load library like this, where we load a new library into memory, it's good practice to just free that library up once you're done with it so you don't cause any errors later on. It basically just says, hey, I'm done with this library. Please go ahead and close it up gracefully. And that's it. That is all we need as far as code for our project. The next step is actually compiling our malicious DLL, and that'll be down here in the terminal. Let me just get to the right file path. So here I am. I have a Linux terminal, by the way, going on in case this looks unfamiliar if you're on Windows. And by the way, if you have msys installed, you can easily just open up msys and follow these exact directions. Looks something like that. And now you can see I'm in here. I'm doing the same thing, except I'm doing it in my bash terminal in VS Code. So you can play along at home if you're using msys by just entering the same commands that I will enter in here. So now that we have our code written, the next piece is to actually compile our code, meaning we're going to compile it into a DLL file. We're going to take our C++ file and our definition file and put it into one singular DLL. And the way we do that is by running G++, which is our C++ compiler. I'm going to add a few flags here. This first one, werr, well actually I'll do all of the flags first and then we'll go look at the manual so you can see what each of these is doing in turn. So that first cards.dll is my output, and then I'm going to pass in my C++ file and my definition file. There we go. So there's our command. Real quick, I will walk you through what those flags are. I've got the manual pulled up here. So the tac werr, all that does is just make warnings into errors. So if for some reason the compilation fails, if I mess something up in the code, it'll warn me or put it out as an error. The static command, let's find that, will prevent linking shared libraries. Basically, this makes sure that our DLL can stand alone by itself. It doesn't need to be linked to other libraries. Lastly, the mdll is specifying that I'm going to generate a DLL. And the last part is just my output file name, which is cards.dll. So let's go ahead and click enter and hope we haven't had any errors. Oop, we do have something, so let's see what I messed up here. This will be good for learning anyway. So pretty simple fix. I accidentally left off one underscore. Let's see if that fixes the problem. It does. Yep, the littlest thing. If it's not a semicolon, it's an underscore. So now that that is finished, let's go ahead and open up our File Explorer, go up one folder. Here's our new malicious DLL. Let's go ahead and move that into, oh, you all probably caught this error earlier than I did. We haven't written our weaponized code yet, so let's do that. So my weaponized code, like I said, is pretty nerfed. It's just going to open up a browser with the system command. It's going to run start. This double quote right here will basically say that it's going to use the default browser that's installed on the user's machine, and it's going to open this URL. So I could also put this into an endless loop, but that wouldn't be very nice to the person I'm doing it to. But you're not limited to just doing like a browser hack or a call with this. You could also do something like running a completely separate program. You could do something like, in fact, let's do two things. Let's run the Rickroll GIF, and then let's start calculator. So that's at Windows System32 calc.exe. And we'll do those two things and we'll call that weaponized. So let's recompile. And let's go back to the folder, make sure we put our new malicious file in there. And so two things should happen when we start our game. We should, I have it open still, that's why it's complaining. There we go. We should see a Rickroll GIF open up in the default web browser. And actually, I don't want it to open my personal default. You could leave that by yourself, but I'm actually going to use firefox.exe because I have that open already. And it should also open up calculator if we've done this correctly. Again, recompile to make sure those latest changes get pushed in there. We need to make sure we put it in the directory where cards.dll is, because remember, that's where we're loading the original functions from. You could rename it if you wanted it to. And now when we run Solitaire any version, whether the modded version or not, I see a Rickroll and I see a calculator. Pretty cool. Hopefully you think so too, and these 4 hours of recording were not wasted in vain. But with that being said, I did promise you a bonus chapter, which I will put at the end here to talk about the resources in solitaire.exe and going back to manually finding those yourself. But besides that, that is the end of all of our objectives. So congratulations if you've made it through this whole video. Really, congratulations. I hope you got a lot of good practice in. If you just skipped around and did the things that you thought were fun or the things you needed to brush up on, that's awesome too. Regardless of why you're here, I'm glad you're here. I'm thankful for you. I hope this helped you in some way. If it did, please leave me a note down in the comments below, or if you have feedback or questions, let me know. Like I said, everything you should need should be in the video description. There'll be a GitHub repo of all the code we've written, the Python script that we wrote earlier with instructions on how to do all of that. You'll have all of your helpful links, and I have totally talked enough for several days, and I'm ready to go back into a hermit status for a while. But before I go, thank you one last time for joining me. I'm Jeff of All Trades, and I'll see you in the next video. All right, if you stayed on for the bonus chapter, I wanted to revisit something from the very beginning of the video, and that was this load icon call out where I was talking about this ID and how you could manually derive what resource that was talking about. And it seems like such a little minuscule thing to focus on, but this was actually pretty enlightening for me, because in the past, I've really always used some other tool to parse through resource sections and executables. I never took the time to fully understand how these are structured. And I found a wonderful resource that talks about how that resource section is structured and how you can manually go through and derive out different resource IDs. Now, what we did in the video earlier is we just took this ID, and the easy button was to search program text for 1F4 for everything, and we were able to find that it was mapped to this GroupIcon resource right here. But we knew that because Ghidra had already gone through and labeled it with the ID 1F4, but we didn't really get to know where that ID comes from outside of, if we search for the scalar, we found it down here mentioned in an image resource directory entry structure. Looks something like this. And if we break it all out, we see a few fields here. Most of them are just filled with that ID. So the blog I found, which I'll include in the description for the video, is the first one I've ever seen that actually maps out in a nice diagram what this resource tree looks like, the whole resource section of the executable file. This is a blog, by the way, from Johannes. I'm so sorry, I don't want to mess up his last name. I'll just say Johannes. Thank you, Johannes, if you're out there still. From 1996 and 97. So this has been around for a while, and yet it's the first time I've seen someone actually draw out how this structure is set up. So what I was talking about earlier with deriving what that ID is referring to manually, in this resource tree, and this is why it gets very confusing very fast, is it's not very intuitive at all like most things Microsoft does. We have these different, what I'll call nodes here at these different layers. He also calls them nodes, leaf nodes, etc., because it is a tree. There's a specific paragraph right here that explains what we're seeing over here in Ghidra, like this field right here. If the most significant bit of the name field is set, the other 31 bits are used as an offset to an image resource dir string use structure. So what does that mean? That means that this value right here in the, the name field, whatever it is 8 4 zeros. Oops, I need to bump this up, maybe. 8 4 zeros 3 8 8. So that highest bit is set, meaning these last bits, the 388, are an offset to the next node in the structure. And what he's saying is that the ID that we mapped here is actually located with this offset right here in the tree. So this is telling us where the resource offset is from the start of the resource section, which is 1008. 000. To recap, all that means is we take everything but the last bit here, the 8 at the end, so the 388, we add that to 100800, and we get to the next node here. So let's do that in Ghidra. We'll add 388. All right, so we've moved down to 388, and we see another image resource directory entry. And this one has a name offset and another name is string value, but this one does not have the highest bit set. Now, we are currently sitting at level 3 of this tree here. The 409 here is the resource language ID, and earlier in the video you heard me say that 409 is mapped to English. If I look that up, there we go. We see it's set to 409 hex, which is English United States. So that's all that node tells us is the language ID, and then it points us through another offset to the actual node that has the resource, which is 520 hex past the start of the resource section. So again, we'll add 100800 plus 520 hex. That'll get us to 520. All right, so going down to 520 brings us to yet another structure. So now we're here that has the size of the resource and the offset to the data. But this offset is not from the start of the resource section. It's actually from the very top of the file. So it'd be 1 followed by 6 zeros plus F188, which of course is just down here at location F188, and it points to the exact same resource we used earlier in the video that had the 1F4 ID. So the reason I wanted to walk through that is just to walk you through how that resource section is set up and how you have to trace through those leaves there to find the actual data. Now, the one piece we didn't see here was the level 1 resource type. If we go all the way back up to this original one, the way we find our resource type is to find the structure in this tree structure that points to this guy right here. So what structure has the offset 158? So let's do a search right here real quick. Sorry, it's actually not 158. It's the directory structure that's right above this. This is the entry that is within the resource directory structure. So we want to find the one that has 148 instead. And sure enough, we find one here at the very top of the resource section with the ID of E, or 14 in decimal. And that is our level 1 resource type. And what that is if we look up what resource type 14 is, it's indeed RT GroupIcon. So again, I know it's probably going to be a very, very small subset of the population watching this video that cares about how to read through these resource trees manually, but that was the first time I'd ever seen a blog that actually talked through it in such plain language that I was able to figure out how Ghidra was able to deduce the ID of that resource. And now you know how you can do it manually in case you ever need to. Thanks for sticking around. Again, questions or comments, let me know here. Brian, go home. You can't keep standing here outside of my apartment. You have to let me go.